I'm gonna give a presentation of pitchfork bifurcation. A pitchfork bifurcation is a particular type of local bifurcation, where the system transitions from one phase point to three phase points. Pitchfork bifurcation have two types, supercritical and subcritical. Firstly, let's look at the supercritical pitchfork bifurcation. The normal form of the supercritical pitchfork bifurcation is x dot equal to Rx minus x cubed. If we replace x by minus x, we get that minus x dot equal to minus Rx plus x cubed. And then cancel the resulting minus sign on both sides of the equation. We get x dot equal to Rx minus x cubed, which is exactly the same as the equation 1. So this equation is invariant under the change of variables from x to minus x. In this case, these points tend to appear and disappear in symmetrical pairs. And now let's look at the vector field for different values of r. For r less than 0, the origin is the only stable phase point. For r equal to 0, the origin is still a stable phase point, but much more weakly, since the linearization vanishes. For r bigger than 0, there is 3 phase points: x equal to 0, x equal to square root r, x equal to minus square root r. The origin has become unstable. 2 new stable phase points appear on either side of the origin, symmetrically located at x equal to plus minus square root r. We observe that for the value of r changes from 0 to positive, the number of phase points suddenly increases to 3. Hence, to help us understanding, let's plot the bifurcation diagram. We can easily see that it turns out to 3 phase points, and for a given positive value of r, the 2 stable phase points has equal absolute value. And now let's look at an example of supercritical pitchfork bifurcation. Plot the potential Vx for the system x dot equal to Rx minus x cubed. For the case r less than 0, r equal to 0, and r bigger than 0. We know that fx equal to minus dv over dx, and in this example, minus dv over dx equal to Rx minus x cubed. By integration, we get that Vx equal to minus 1 over 2 Rx squared plus 1 over 4, the first power of x. And let's look at the vector field for different values of r. When r is less than 0, there is a quadratic minimum at the origin. At the bifurcation value r equal to 0, the minimum becomes a much flatter quadratic. And for the condition r bigger than 0, a local maximum appears at the origin, and asymmetric pairs of minima occurs on either side of it. Now, let's look at the subcritical pitchfork bifurcation. The normal form of subcritical pitchfork bifurcation is x dot equal to Rx plus S cubed. Let's see the bifurcation diagram of it. The non-zero phase point x equal to plus minus square root r are unstable and exist only below the bifurcation r less than 0. It is opposite to the subcritical pitchfork bifurcation. More importantly, the origin is stable for r less than 0 and unstable for r bigger than 0. Let's see the higher order terms. In real physical systems, higher order terms are more likely to be presented, assuming that the system is still symmetric under S2 minus x. The first stabilizing term must be the fifth power of x. Thus, the canonical example of system with a subcritical Pitchfork bifurcation is x dot equal to Rx plus x cubed minus fifth power of x. Let's look at the bifurcation diagram. And by looking at the bifurcation diagram, we observe that firstly, in the range Rs less than R less than 0, two quantitatively different stable states coexist. And secondly, the initial condition S0 determines which phase point is approached as t goes infinity. Thirdly, the origin is locally stable but not globally stable. Fourth, the existence of different stable states allows for the possibility of jump and hypothesis as R is varied. Suppose we start the system in the state x equal to 0 and then slowly increase the parameter R. Then the state remains at the origin until R equal to 0. When the origin loses stability, now the scientist node will cause the state to jump to one of the large amplitude branches. With further increase of R, the state moves out along the large amplitude branch. If R is now decreased, the state remains on the large amplitude branch. Even when R is decreased below 0, we have to lower R even further to get the state to jump back to the origin. Fifth, the bifurcation at Rs is saddle node bifurcation, in which stable and unstable phase points are blown out of the clear blue sky as R is increased. That's all of my presentation. Thank you for listening.